they start running people for submarine. Then people just write if you are the first time, you can just write I'm the first time that and I get some assistance. So you just when you were looking at this Warsaw,
One, two, three. I'll probably have to start chairing my own session.
I can share it for you.
1, 2, 3, Milena.
Using the opportunity to chair the beginning of the session, I will give the microphone to the real chair of the session.
Hello, my name is Katarzyna. I will be chair lady of this session, and the first speaker is Lukasz Wyrzykowski.
Thank you very much. Oh, sorry, I just need to move this window away. All right, going into the view. Hello, hello. My name is Lukasz Wyrzykowski. I work on Gaia and other stuff, time domain related stuff, but Gaia has been my kind of main source of scientific life over the last 20 years or so. We've been just recollecting, our memories from the old days when it all has started a long time ago in a different world. Anyway, here we are. Gaia is perfectly operating, and now we can actually take and enjoy all the fruit of Gaia. And my personal scientific interests are microlensing events, and this is what I've been working aside of Gaia alerts and time domain stuff and follow-up. I've been also working on microlensing events in the Gaia archival data, and this is what I'm going to report to you now. So the title of the talk is Microlensing Events from All Over the Sky from Gaia. This is almost more or less the title of the paper we published as part of Gaia DR3. So there were something like 40 papers, and this was one of them. Right, and it doesn't move. Sorry. Right. No. I'll be fine. So that's a black hole, right? You have to believe me that it's there. So this is what scientifically what drives all this research in microlensing, at least for me. I know there are people doing some planets, boring stuff, and some roundworms or binary systems, boring stuff. Black holes are probably most exciting, at least for me. Okay, I'm biased. But actually, originally, microlensing started with this idea that microlensing is the only method which can give us black holes. And I mean black holes which look like this, right? There is no companion, there's no other star revealing the presence of a black hole. There's no accretion going on. There are no those crazy jets we've seen earlier today. So it's there, right? It's a free-floating black hole somewhere there, interacting solely with the space-time. And we use that feature of a black hole that it interferes with the space-time. So we're using microlensing for this. And if we look at the picture of black holes and neutron stars we know so far, it's actually very, very scarce. So I like to show this picture, first generated by the gravitational wave people. Actually, gravitational wave discoveries, first of all, it was a technical breakthrough, but also scientifically, it revealed very interesting population of compact objects. Okay, of course, we did see them merging. So there were two, and then they turned into one. So that's not exactly what we are after, but still, eventually they become single black holes, right? But the funny thing is that the discoveries in gravitational waves, they tend to see massive black holes, massive compact objects. And so you see the blue dots here are the components of the system, and then the end product of the merger seen in gravitational waves. And you see there is a lot of black holes with masses of around 50, all the way up to 150 solar masses. We are entering the regime of intermediate mass black holes, actually, with gravitational waves. And there is less of them at lower mass end, but I just guess this is the observational bias. It's easier to see massive ones. And then this is all combined with what we knew before gravitational waves. So there is this, it's a very small collection of something like 50 systems in binaries, where there is one compact object and another star. So we know indirectly about a black hole or a neutron star there. So you see these, they look like kind of distinct populations. So people start to think, okay, maybe some of the massive black holes we see in gravitational waves there are due to dark matter. Maybe, why not? And then if there is the mass gap, people were seeing in the electromagnetic compact objects, is it there? So the mass gap between most massive neutron star and the least massive black hole. So we see these questions, these question marks, they're there. And these are very interesting astrophysical questions we can answer by looking for black holes. And microlensing can contribute to that very picture with additional points. And actually, we are probing slightly different populations, so we can say way more about the underlying astrophysics. And microlensing is marked with red, so red dots, the very bright red, let's say. That's a single black hole found so far, right? So this is the very beginning. Actually, a few months ago, this picture, I was showing it multiple times, so there was no red dot. So this is a very fresh, still warm red dot on that picture. So you see the papers were published in 22. There are 3 papers about that one. You would be fine just reading the last one. So this is a 7 point something solar mass black hole detected with microlensing. I'll get to that in a second, a little bit more. So how to find a black hole with microlensing? So to find a black hole, you need to prove you have a large mass and you have a dark object, right? Easy. So in order to measure the mass, you need to solve this equation where the only thing we know is kappa, it's a constant. And then you can measure, you have to measure the size of the Einstein radius, theta e, and then the parallax, microlensing parallax vector. And then for the distance, you see where this parallax, how it's defined, actually it comes from that equation, the pi e, the Einstein parallax, the microlensing parallax. So we measure the distance, measuring those quantities, and then we measure the flux. And flux comes from the light curve. So you can get those quantities we need to solve those equations from various methods: photometry, astrometry, spectroscopy, and I marked them color-coded, more or less. You can figure out what comes from predominantly which method is best suited for that. So the thing is that you can use variety of instruments. For example, for photometry, you can use surveys like Howil. They've been monitoring for dozens of years millions of stars, and you have exquisite photometry. You can use Spitzer for that. You can use Las Cumbres Observatory. You can use a follow-up network. Why not? Gaia alerts and then a follow-up network. You build photometry. And then in future, we'll have Vera Rubin Observatory and LSST giving us photometry. For astrometry, you can go for things like VLTI, adaptive optics, James Webb probably as well. And then in future, a couple of other instruments. For spectroscopy, you need to probably go to very big machines like VLT, Gemini, SOAR, SALT. This is what we've all been doing. But you see that all these methods, they have one word in common. This is Gaia, right? Gaia is actually giving you all of those 3 components. So at least in theory, you can get all the necessary ingredients to find a black hole from Gaia alone. This is not exactly true. You need to subsidize these measurements of Gaia with those instruments. That's why we have the follow-up network, right? You know, the Gaia sampling is sparse. We take spectra of much higher resolution and much fainter objects with big instruments. But in principle, Gaia is the machine for finding black holes. And that's what we've been doing, and this is the main focus of this work. So I mentioned this first discovery. So this is the first isolated black hole found through microlensing. This was done with Hubble Space Telescope and the Howil data. So you see on the right, there is this beautiful microlensing curve I showed here. This is ogle data. This is MOA data. This is another microlensing survey. There is a lot of contributing telescopes to that. So you see a very densely sampled photometric light curve. And then on the left, the very left, you see the observations from HST. So what you measure with HST, you measure a tiny displacement of the source. Not only the brightness change, but also a displacement. And the displacement is of order of 1 milliarc second. So with HST, you can do that. But with HST, you need to know where to look. So this event happened in 2011. And then since then, this event was observed for all those years. You see the scale here. It's been observed for 6 years to find one. There was a set of other events, of course, observed, but then they turned out not to be black holes. This was the only one which turned out to be due to a black hole. So this is a very time-consuming experiment and very risky because you don't know if the event you've decided to follow with HST is actually a black hole. So what we need a survey which observes all of them and gives us HST quality astrometry for all of the events. And again, as I said, Gaia is the thing. So just a few slides just to get you on the same page with Gaia. It was mentioned multiple times, but I will emphasize that Gaia is monitoring constantly 2 billion sources. And microlensing probability is something like 1 in a million. So you can imagine how many events we can discover with a survey which is monitoring 2 billion sources. This is the focal plane. I don't believe it has been shown already, but this is quite unique for Gaia because we get both. Do I have an animation here? Yes, there's an animation. This is how it goes. That's how Gaia operates because it spins all the time, and it's observing stars. If they appear there, that's why it's so suitable for alerts. If there is something new, then it can detect it. And then Gaia measures at all those CCDs. They give photometric measurements. They give astrometric measurements. Then we get these low dispersion spectra. And then for some brighter cases, we also get radio velocities. Here I have an animation showing how Gaia scans the sky. Hence, we have a very certain pattern of the light curves. As I said, Gaia is monitoring 2 billion sources from all over the sky, right? But this comes with this particular pattern, which is coming from the fact that Gaia is avoiding the sun, of course, and the spin axis is revolving. You see these dots running all over the sky. And this is the color coding shows how many points you get per source at a given location of the sky. So some parts of the sky are more privileged than others, but this is simply due to the pre-designed scanning pattern. Moreover, we can actually use some prediction tools. You can tell where Gaia is going to look tomorrow or in a month's time or in next year. So if you want to observe simultaneously, you can do that. That's the advantage of it. So in general, we at least in the nominal mission, which is from 2014 until 2019, we actually already got something up to 200 points per source. Some places on the sky, they get as low as 40, and this is the equatorial map, so you can imagine where the galactic plane is. Unfortunately, the very center of the galaxy is the least sampled part of the sky. So this is where other microlensing surveys are actually doing a great job. So we let them do their job, and Gaia is taking over the rest of the sky, which is most of it. So Gaia is measuring parallaxes through that simple parallax phenomena, just observing from different positions on the orbit that is on together with the Earth. So it's measuring actually the positions of stars, and then all the stars, they move with the parallactic motion. They also have the intrinsic proper motion. And for most of the stars, what you see is this wiggle. So this is the typical motion of every single star on the sky, unless it's microlensed. If it's microlensed, then on top of that, you get an additional motion of the source position which we are actually going to use. And here you see the plot showing the accuracy of the Gaia astrometry. So at about 18th magnitude, Gaia is expected to have 1 milliardsecond precision. So this is the precision I showed you HST they got from HST for that one event. And all the way down to 18th magnitude, Gaia is giving us better than 1 milliarsecond resolution, accuracy. So we looked for events in Gaia data. So this was Gaia DR3. So the time span was between 2014, 2017. And as mentioned yesterday by Laszlo, there were many other types of variable stars and time domain objects being cataloged. So microlensing events were among them. So there we found 363 events, and this is their map on the galactic plane. You see they come from all over the plane, mostly from the galactic, from all of the sky, of course, but mostly in the galactic plane. This is where the lensing probability is the highest, hence this is quite natural. But we also see some other events from other directions, which is actually very, very interesting. So this is a web page where you can actually, my private web page where you can have a quick look at all the events. So what we published not only a catalog, but also their light curves in 3 bands. So G, integrated BP and integrated RP. So we have color light curves for all those events, and these observations are simultaneous. Yeah, and also there is actually a very nice essay written by Michael Perryman. You can have a look. Michael Perryman was one of the founding fathers of Gaia a long time ago. So he was intrigued by our catalog, and he wrote a very nice essay about this. So of course there are other microlensing events being found by Gaia, and then I think it's gone. It's dead. Thank you. Can someone replace the batteries there? Okay, I'm back again. So Simon showed his paper, and there is additional bunch of about 300 something events found in a kind of overlapping period, but also later. Gaia Alerts is finding microlensing events in real time, right? But we only started finding microlensing events in Gaia Alerts from about 2016. That's why many of the events from DR3, they are new events. They were not seen before. Some of them were found by other surveys, but still there's about 100 of events which were seen only by Gaia. And now we are more or less finding 1 to 5 new events every week. And here you see a distribution on the map, but I also overplotted the Gaia Science Alerts events on top of that. So you see they come from all over the place, including the mysterious gold belt, which is an interesting idea. We're trying to explore if there is any connection of some of the microlensing events with the gold belt. This is not Andy Gould, and this is Benjamin Gould from 19th century. Okay, so when we compare the events with the old survey, for example, we see the completeness of Gaia is actually, of this catalog, is actually fairly low for the galactic center. It's about 20 to 30%. But I was saying that the cadence is low. There's not many data points there, but it's about 80% in the disk region, so the rest of the sky. And the recovery of the parameters is actually also pretty good, but it actually goes both ways. Some of the events have different timescales in Ogle, and some crazy timescales in Ogle, and sometimes they have crazy timescales in Gaia. But there is some overlap, and Katarzyna Kruszyńska, she's going to show you some of the interesting stuff out of it as well later. The contamination is very low. This was our aim, to make the catalog as pure as possible. The contamination with variable stars. If you have just 3 years of data, you might be tricked by some long period variables, boring stuff. But they sometimes they look alike microlensing, so they may mimic them. So we were trying to keep it very low. And YSOs as well. We had some suspicion on some of them in that catalog as well. You can actually study the lenses in some of the cases. If the lens is luminous, So it is actually well visible in the light curve in the model of the event. And you can actually for the luminous lenses, which are not that interesting, because stars are lensing more frequently than black holes, but we can fairly quickly rule out which events in our catalog are due to stars and not black holes. But you can place them on a color-minded diagram, and then you can see which population they come from. Either on the right is the bulge or the disk here on the left. I just flashed this event very quickly. That was one of our most spectacular discoveries with the Gaia Science Alerts, actually. And there was a Gaia Image of the Week a year ago. And there was a talk by Kruszyński on the previous workshop last year. So have a look there. But this is where the Gaia astrometry has been shown for the first time ever for a microlensing event, and we were able to show that Gaia is able to detect this tiny displacement. But this event was so crazy. I think we can easily say that this was the craziest microlensing event ever found. And this event is the first one in our catalog. We sorted our catalog, actually. We decided to give up all those long telephone numbers from Gaia source IDs and have our own nomenclature. So we call them Gaia DR3 ULens, and then a number. And the numbers are sorted by the baseline magnitude. So this one is the very first on the list. So this was the brightest event we found. Interestingly enough, no one has ever seen this event. It happened in 2015, and only Gaia discovered it later on. So Maja did a very nice study of this in her paper, and she's going to present it soon in this later in these sessions. Of course, there are other events found by Gaia Science Alerts. I will just flag this one, and Kasia will talk more about this. I call this one, because I like the name here, Gaia 22 BPL, and we call this Bogdan Paczyński lens. So Bogdan Paczyński was a Polish astronomer who was actually a founding father of microlensing, at least for the Polish community. It all started in the 90s. So he has his own lens now. It's actually a very interesting lens. It's very bright. As you can see, it's 12 or 11th magnitude. And FNR has been shown before, but I really like to show this again, that we have data from Gaia, data from beautiful follow-up, from many of you who are here, also from TESS. And we're working on the model. This is one of the models shown here. We think it's a fast rotating binary, similarly as Gaia 16AYE, but this is not a caustic crossing. So this one is extremely difficult to model. And also because this is very bright, we will get Gaia astrometric measurements for that one. So that will be solved, not yet, but we're still, at the moment, we're actually struggling, telling more about this event. And we got very nice spectra for that one. And we know this is X-shooter spectrum we got for this event. Still, we're struggling to tell more about this event. So I have a quick summary here that Gaia is the only survey providing time series. Let's do that again. We don't have any. That works still. Okay, so time series of photometry, astrometry, and spectroscopy. It comes from Gaia just in one place. It's perfect for microlensing. And the precision of Gaia is below 1 milliarcsecond. That's what we need. So this is perfect for microlensing. So we have already about 1,000 of events and more to come. And then the epoch astrometric measurements are going to be available for all sources in DR4, which is coming in 2025. So the work on it has already started. We internally within Gaia Consortium, we've seen the astrometric time series. They look beautiful. I promise there's going to be a lot of fun with that data. And then events from Gaia Alerts, of course, they require follow-up, but we know that. That's why we are here. And Gaia astrometry will be the key to find black holes among Gaia observed microlensing events. And I will just mention briefly that there is a plan for next Gaia near infrared in 2050 for younger people here in the audience maybe. So lesson learned here, astrometrically, that will be another revolution, and that will be perfect for microlensing, because that will be an infrared mission going much, much fainter, and there will be thousands of microlensing events there, and black holes will be just flying out of it. I'll just finish with this advert, Gaia DR3. We're collaborating with a company, actually in ESA as well. So there's going to be a Gaia related citizen science project, which is about to start in December. So microlensing events will be one of the things which will be discoverable in the Gaia data by anyone. So it's like Galaxy Zoo, I'm sure you know that. So that will be making Gaia time series available to citizens and doing science out of it. And I'll just finish with an animation. Oops. And thank you. Thank you. Thank you.
Thank you, Lukasz, for your talk. Questions here from the audience? Anybody from Zoom?
I know.
It's a bit flippant, but can you stand a little bit to the left so I can see the movie properly? It's very beautiful. Can you do one for the whole alert stream? It's based on the surrogates.
It was done by Sergey.
Okay.
Well, this is only for microlensing. This was done for the Gaia DR3, actually by Maja and her boyfriend. So, and I've added the music, so on YouTube you can hear it as well.
It's very beautiful.
Thank you.
Okay.
Right. No more questions.
Okay, thank you very much,
Thank
Lukasz. Next talk, we have a little bit of change. It will be Uliana Pylypenko talking about microlensing events from Gaia also.
I have to stop this, sorry. And I need to find your...
Okay, no more questions. Okay, thank you very much, Lukasz. Next talk, we have a little bit of change. It will be Uliana Pylypenko talking about microlensing events from Gaia also.
Where is it? Stop this, sorry. No, I lost it. Now we are hearing ourselves. I know, I found it. Good. Now I need to find your slides, Uliana. Sorry. You can start talking.
Okay, well, maybe I will tell that my name is Uliana. I don't know, said already. I'm from the University of Warsaw, and I will tell you a little bit about the microlensing events detected by Gaia alerts, which I modeled, and in general, why it is cool to model this kind of stuff. Just a moment.
You should be able to change. Okay.
Okay. So I think most of us get idea of what microlensing is. Actually, here is the scheme of normal lensing, not microlensing, but it's a bending of light rays by a foreground object. And what I really wanted to emphasize that we can detect microlensing in two ways, photometrically and astrometrically. Photometrically means we measure the brightening of the source, and astrometrically we detect the shift of the centroid of images which appear when the source and the lens go close to each other. And we really like to have both photometry and astrometry for a single microlensing event, because as Lukasz already mentioned, we can determine mass of the lens and distance to it. And in general case, we have the microlensing parallax from photometry and theta E, the Einstein radius from astrometry. And we like massive stuff, as we said already. So we like events with big theta E and small PE. And these are my events, which I modeled. They occurred more or less here. Here's the zoom. So they are called Gaia 17 BDK, CAH, BBS, and BEG. They were detected by Gaia alerts, and they are quite interesting because we can get astrometric data in future for them. So what I did to them, I used the PSPL model, or point source point length model. These are general formula describing this model. I also calculated the blending parameter and the magnitude in baseline. I used a Markov chain Monte Carlo method, and some OGO data were available for some of these events. So this is the first one of them. It looks quite ordinarily, I would say. And here are the parameters distributions. This event is not very long, only 55 days. Gaia 17 CAH looks quite similar, but the parallax effect is more visible here because the black curves are the models without parallax, and the magenta ones are black ones are with parallax and magenta ones without parallax, just to show the effect of it. And actually it has also similar time scale, so quite short. Gaia 17 BEG is a little more interesting because here we see the significant parallax event, parallax effect, and it is also longer because it's lasted more than 100 days. And Gaia 17 BBS is the most spectacular one. So because its magnification, its brightness rose on 5 magnitudes, and its time scale is about 159 days. So it's quite promising. So what can we do now? Well, actually nothing special until we get astrometric data, but we can at least estimate is there something interesting in this event. So as we know, all of these events are situated in the galactic bulge, and we know some parameters of the galactic bulge, so we assumed the values we missed and estimated the masses and distances. Here was what we get. Gaia 17 BBS is really the most promising one because its mass is more than 3 masses of Sun. And other lenses are quite, their masses are less than 1 solar mass. And also, we could estimate whether these lenses are dark or luminous. We just compared the real magnitude of the lens with the magnitude of the main sequence star of the same mass and of the same distance. And in the result, we got that we have 2 main sequence stars, low mass, and a white dwarf in BEG and a black hole in BBS. So maybe we would like to have astrometrical data for BBS in the first place. And also, we simulated the astrometrical data we can have from Gaia, that is the centroid shift. So here are centroid shifts for Gaia 17 BDK CAH, BEG, which is quite crazy, and BBS. And also here are the positions of the source and images. The source position is the red line, and the images are blue and yellow line. So again, BDK CAH, BEG BBS. And just to summarize, with Gaia alerts and Gaia in general, it's we can model kind of hundreds of similar events, and that means that we can explore hundreds of isolated objects, and hopefully we'll find something really interesting there. So thank you very much.
Thank you very much, Uliana. Are there any questions from the audience first? Okay, Mila. So when can you get astrometric data?
I hope the first occasion will be with the fourth data release of Gaia, because I think there will be astrometric data.
For all the sources, right?
I don't know if for all, but I hope for BPS at least.
Okay. Anybody? Okay, second.
There's one on Zoom.
Yeah, well, go for it.
You mentioned parallax. So do you have any plans to measure parallaxes, maybe with JWST or for future events?
You mean parallax of the source?
Yeah, well, yes, of the light curve simultaneously between the Earth and then L2.
Well, I didn't think about this yet, but this is quite an idea. I was kind of focused on astrometry because I want to learn it well.
Okay. Anybody else?
Katarzyna,
So another question from Zoom.
there are actually two questions. Etienne is asking, how do you estimate the mass of the lenses?
Okay.
You said that, yeah.
This will be a bit long. Okay, so this is the formula for the mass of the lens. Here we have theta e, the Einstein radius. Kappa is just a constant, and the e is the microlensing parallax. Microlensing parallax is kind of the sum of squares of these two parallax components. So we have it from the photometric curve. And to estimate the Einstein radius for now, here is the formula on this slide in the bottom. We can calculate Einstein radius in another way with astrometric data. For this, we need relative motion of source and the lens, but this is less universal than astrometric microlensing because we can do this for example, for dark lenses. But anyway, we know how stars move near the bulge. So I just suppose that it is 4 micro arc seconds per year. And this is just a combination of dE, which we have from the photometric curve, and μ. So here where we get the Einstein radius, and that's it, maybe. And also, I suppose that we have the bulge on the distance of 8.5 kiloparsecs. So this was the assumption for a distance for the source. And here we have the distance to the lens.
Yeah, so at the end says, thank you. I would just add, this is a simplification. And of course, a more detailed model of the galaxy
yeah, sure.
will be added. We have tools for that, but there was not yet time to finish that. But well, for an estimate, it was enough.
Yeah, all these estimations are quite rough, but that's all we can have in this moment.
And then Valerio Bozza is asking, did you take into account the finite source effects in the predicted astrometry for VBS?
No, not yet.
But do we actually see any finite source effect? We didn't look into that. But the model looks okay, so probably there is no finite source effect very much pronounced in that event.
Yeah, but all of these curves look quite okay on this.
There is no data at the peak.
Yeah, but here it is.
Here there is.
Yes, so it doesn't look like there is significant finite source, so we didn't take it into account.
Okay.
Thank you very much, Uliana, for your talk again.
And the next speaker is Paolo Rota from University of Salerno, talking about Gaia 21 VLX event. Thank you.
Okay. Hello to everyone. I'm Paolo Rota from University of Salerno. I'm very happy to be here. Thank you to the organizers for inviting me to this event. This talk I will show you my preliminary analysis of Gaia 21 BLX. I'm working with Professor Valerio Bozza, who is online on Zoom. So,
Sorry again.
Okay. The talk is about the microlensing event Gaia 21 BLX. We work with the collaboration with the Omega Key project. So see the Etienne's talk tomorrow, as I found. And just a brief review about microlensing. So, okay. We know what is microlensing, and we have a microlensing event when the light of a source is bent by the lens when it's directed to the observer. We can calculate the total flux of microlensing event by the following equation, where AT is the magnification, Fs is the source flux, and Fb is the blend flux, that is all the flux that is not affected by microlensing. The parameter scale is the Einstein angle, as you can see by that equation, where we have the mass of the lens and the distance of the lens. That are the two main parameters that you want to know in a microlensing event. In the simplest case, we can analyze the microlensing event with a single lens, where we need the four parameters: the Einstein time, the time of a closest approach T0, the impact parameter, and the finite source effect, when we can derive it. If we have another lens, so we have the simplest case of a binary lens static system, we need to include three more parameters: the separation between the two lenses in units of theta e, the mass ratio between the two lenses, and the angle between the second and first lens and the source trajectory. But we can include also the high-order effects, such as the parallax with the two components in the north and east direction of the parallax vector, and the orbital motion. In the simplest case, we can assume a circular orbit with three parameters that are the three components of the projected angular velocity. We can also include the Keplerian orbit, a triple lens, a binary source, but for this event, we can stop to the orbital motion. How we work to this event? We start from to analyze the event with the RT model platform based on the VBBinaryLensing code. See also the Valerio talk later. From this, we obtain preliminary solutions from about the event. And from this, we start a Leverberg-Marquardt algorithm in order to minimize the chi-square of the cases. And after we run Markov chain at high temperature in order to explore all the space parameters. And we record all the minima that we find, and we do another Markov chain step by step until reducing the temperature until we find the best solutions. In this case, we obtain 4 competitive solutions for this model: 2 binary closed solutions with parallax and 2 binary wide solutions with parallax. We have the closed solution when the parameter S is less than 1, while for wide solution we have S greater than 1. We denote this 4 solution with this names. The R stands for, we obtain the R models by the reflection of 2 parameters, U0 and alpha, because there are some degeneracies in this type of events. But with the parallax, only with the parallax, we have a good fit of the event. But in this case, we want to constrain better the parallax value, also the error. So we include also the orbital motion. So the improvement of the chi-square, as you can see, is very, very low, but it's necessary. We assume that the LO wide is the best model. It has the best chi-square and also the best improvement of chi-square starting from the parallax model. This is the table with all the parameters. As you can see, the orbital parameters, we can assume them with 0 in the error. So we use it only for constraint the parallax, as I said. And we can say that the blending value, denoted with the B, F, are very, very high. Probably the lens, as Lukasz said in the previous talk, the blend can be assumed as the light of the lens. We also obtain some analysis of the magnitude and colors. And this is the light curve of the event. We have 3 telescopes, including Gaia. And on the right, we have the cosine configuration with the source trajectory in the frame of the lens. Now, next step, we want to derive the physical parameters of the lens. So, our hypothesis, we assume that the blend flux is the flux of the lens. And starting from this, taking the Gaia parallax from the 3rd degree release with a RUV of 1.18, that is more or less acceptable, we assume that this parallax is the flux weighted average of the parallaxes of the lens and the source. In this way, we can obtain separate information on the lens and the source. How we do this? Starting from the G Gaia and G bands, we use the early data release, the 3rd, and we use the relationship to convert from those bands to the V magnitude, to V band, because we can use the mass luminosity relationship in V band and the Redden interpolation and the extinction law of this work to construct a plot where we have the magnitude in function of the lens distance. We derive the magnitude of the lens in V band, that it has this value, and we construct this plot. The blue plot is the V magnitude in function of the distance, while the black horizontal line is the V magnitude obtained for the lens for this model. The intersection of these two plots give us the lens. That is more or less 1.1 kiloparsec. Once we obtain the distance lens, we can obtain also the mass. As you can see, is 0.75 with 2 separate masses for the 2 lenses of 0.66 solar masses and 0.15 solar masses. Probably we have a low mass binary system. I know that the error is very, very high, but in principle, this algorithm can be good because we have also the astrometry. We simulated the astrometry also with the VBBinaryLensing code. And the blue trajectory is the source trajectory. In this case, we have a fixed frame. So there is no orbital motion, but we put the we put it in the trajectory where we have the orientation of the lens during the microlensing event. In orange, we have the astrometry calculated with the VBBinaryLensing code. The 2 brown points are the 2 lenses. Here we have in unit of arc seconds. As you can see, in the bump, there is few Gaia points. So, in principle, we can say that microlensing does not affect the Gaia parallax, whose data are taken before the microlensing event. As you can see, the Gaia baseline is very, very long. So, since we have also a microlensing event very short, of the order of 90 days, the hypothesis that we did can be good. So, what are the next steps? First, we want to improve the models in order to reduce the errors and the chi-square of the models. And this way we can derive the lens mass, but also the lens distance with more precision. And in consequence, we can derive also the properties of the source. After we check if all the models can be good, because we try with the best model only, but the other model can give us interesting results, but also unphysical results. So if we less models we have, happier we have, because the generality is not good. For this, we need the spectra that in the next months, I think it will be available. And once we have all these things, we can start to write a paper. So, conclusion, with this work, I want to emphasize that how Gaia parallax is important to estimate the properties of microlensing event. This is not always the case, as you can see in the Powell's talk, because in some cases the Gaia parallax is not, we don't trust to the Gaia parallax. So in this way, we can have the information on the lens, on the source, and we can have more information about the galaxy dynamics and also on the stellar population. And thanks to Gaia, we can have also more exoplanets to detect by microlensing, and we can improve also the demography of exoplanets. That's all. Thank you for the attention.
Thank you very much, Paolo.
It was very fast.
First, Lukasz, or
Yeah, that's my question. The source distance, have you assumed?
3.5 kiloparsec, but the error is very high.
But how do you know that?
Once we obtain the lens distance and the mass distance with the parallax, we can derive also. Yes, but the error is very, very high. So with the spectra, I think we can.
But that would be an interesting experiment. We talked about it already.
Yes.
In the past, but then the spectrum, even from salt, well, it's a low res, but you should be able to see, you have three sources of light. You have the source and a luminous binary system, right? So you might actually see three sets of lines in the spectrum.
Yes.
That would be cool.
Yes.
Any questions from Zoom?
Not yet.
Okay.
And from the audience? Okay, Milena? I was wondering about this binary system. You said the estimation of mass is 0.6 and 0.15, right?
Yes, a low mass binary system.
That's a very low mass.
Yes, but it's very near to us, 1 kiloparsec. But the error is very, very high. As you can see by the error in the mass is 0.56. So probably it's a low mass binary system, but with more information about the spectrum with the source, we can obtain more information.
Okay, any more questions? I have one concerning spectroscopy. Can you share some details regarding what spectroscopy do you want?
With the spectroscopy, we can obtain some information about the lens, the source, sorry.
No, I mean from where you will take this.
And I hope with salt, I don't know.
So with salt, let's go.
Yes,
Okay.
with salt.
Thank you very, very much, Paolo. The next speaker is Katarzyna Kruszyńska. She will be online and she will share some details concerning Gaia alerts and Microlensing event.
I hope she's there. Well, I don't see her online yet. Maybe we can have Kornel.
Okay. Kornel, are you ready?
That's last slide. Kornel has 3 slides.
It's more than.
Well, you can use your own laptop. You can zoom through your laptop and then just show it there. It'll be quicker.
I think presentation is still in progress.
Still in progress. So who do we have next?
I sent it to your Slack.
Okay, it's there. Bravo for Kornel. Okay, so we had a little bit shift in our plan. The next speaker will be Kornel, talking about Gaia 18A.
Well, and now I need to open it. Would have been quicker.
It's in PDF.
Yes, but you send it to Slack, which I don't have.
I was in hurry.
Hmm?
I was in hurry.
Sure. It's opening. There it is. Którym to workspace było?
Naszym chyba normalnym.
You can start talking. Introduce yourself.
So hi, my name is Howil, and I am a student at University of Warsaw, and I will talk about Gaia 18AGZ Microlensing event. And now I need my slides.
Yes. Why? You have a board there. Sorry, I have it, but I need to download it from Slack.
Can I get this magic pointing device?
Paolo has it? No, it's there. Yeah. Almost there. Almost there. And it's coming.
Nice.
There you go.
Okay, so now some basic info about this event. This event was alerted on February 2018. And as you can see, it is approximately 20 degrees from the galaxy center. And it's a very dark event with baseline around 19 magnitude and with 17.5 magnitude in the peak. We have obviously data from Gaia as well as from ZTF, but we have follow-up from SMARTS, Observatory, Pirate, Uliana, and Terskal, but only Gaia, ZTF, and SMARS had that data both in peak and in the baseline. And since we need data in the baseline to model this event, we only used data from these three sources. We also have follow-up from X-Shooter and from spectral analysis. We know that the source star is K4 giant with absolute magnitude minus 1.8 magnitude and with huge extinction in V8 magnitude. From this, we estimated the distance to the source star to be around 11 kiloparsecs. Here you can see two light curves. On the left is the one with only Gaia data, and on the right we have data from Gaia, ZTF, and SMARTS. As you can see, follow-up data is not a good quality, and it really disrupts our model. We have two solutions for this event, one with positive U0 and one with negative U0. We calculated three models with different sets of data used, and model with only data from Gaia and Gaia plus ZTF agree with each other, but if we add SMARTS, things are starting to go ugly. As you can see, in all of these solutions, we have huge TE around 400 days, but blending parameter in last model is very different from first and second. Here we have negative solution, and it's the same story. We have huge TE and a blending parameter in Gaia plus ZTF is agreeing with each other, but model with smudged data is really blowing up since FS can be greater than 1. Using density model of the galaxy and velocity distributions, we estimated mass and distances to the lens for both solutions, and we see that mass is greater than 1 solar mass, and for one solution distance is 4.5 kiloparsecs, and from the other 6.4 kiloparsecs. And probability that the lens is not a star but a dark object is between 40 and 80–90%. These huge differences are due to huge extinction. So in summary, this event is very long, around 400 days. We have low parallax, low blending, what means that the lens could be a dark object. 1.15 solar masses, distance between 4 and 6 kiloparsecs. So the lens is probably a star or a white dwarf. We don't know because extinction is so huge. And follow-up data is really bad quality, so it doesn't really help to model this event. Thank you.
Thank you very much. Do we have questions from Zoom?
No, I don't see.
Okay. And do we have questions from audience? Anybody? Come on, we are jumping.
When you go back to your if you go back to your models where you had Gaia plus ZTF and
with
plus
parameters,
yeah, and the smart data, and you said when you add the smart data, they're blowing up the solution. Look like the errors on everything apart from F is a lot smaller when you add the smart data.
yes, that's true, but this solution can't be physical because that would mean that a lens is giving negative light. This is not possible. It's only mathematical model that works, but it's not physical.
Thank you. So this is due to extension. When you are adding additional data, it is that the model is getting worse.
I think it is due to quality of the data.
I see. Rather.
Yes.
Okay. Thank you very much. Anyone else? If not, Kornel, thank you for your talk. Okay, and our last speaker of this part of the session is Katarzyna Kruszyńska with Gaia Alerts.
Hello, everyone. Sorry, I have to move my cat.
Hello.
Hello, can you hear me?
Yes.
Hello? Great. Okay, let me just share the screen. Oh, no, wait. Maybe I'll stop sharing for a second, sorry. I have to find my presentation. There it is. Okay, can you see my screen?
Yes, we see.
Okay, great. So hello everyone. My name is Katarzyna Kruszyńska. I am a PhD student at University of Warsaw. And today I will talk about microlensing highlights from Gaia Science Alerts. I'm not the first speaker talking about gravitational microlensing, but I will give a short summary. Gravitational microlensing has two effects, astrometric and photometric. The one that we focus on usually is photometric, where because of the, sorry, I have to take care of my cat. Because we have a source, massive lens passing in front of the distant source within our Milky Way or its neighborhood. The light of the source is magnified due to Einstein's general relativity. This causes a distinctive change in the light curve shown on here on the bottom left. And we also can observe such effect in astrometry if we have precise enough measurements of the position. So because during the microlensing event, the image of the source is split into two unequally magnified images shown here with blue such blue shapes, the center rate of light shifts, and it's well, if we don't have a parallax movement and our source only moves along the straight line, it will have a distinct shift. And this is important because for Gaia, because Gaia can observe not only the photometric effect, which many other photometric surveys can do, but because it's an astrometric machine, it has capabilities, proven capabilities of observing astrometric effect. So just to shortly reiterate, this is the summary of the Gaia strengths for microlensing, which is for as I mentioned before, astrometric time series. So for possible detection of astrometric microlensing effect, and it also observes the entire galaxy in 3 bands, which is not uncommon because for most surveys, because they are ground-based. Additionally, it also provides low-resolution spectra, which are useful for classification, which I will be talking about later. However, Gaia, as you probably know, has a very low cadence, especially it's on average, it gives you 1 point per 30 days. And especially this cadence is even worse in the galactic bulge. However, we can facilitate, thanks to the work of people connected in the optical ORP networks, we can make those problems smaller. Currently we have, Lukasz talked already about the catalog of microlensing events from the entire sky. And I will talk about microlensing events found in a different way through Gaia Science Alerts. So you probably know this webpage very well. And using the alerts published through Gaia photometric alerts, we've managed to find over 400 candidate microlensing events pretty much by now. And this is the image of the sky. As you can see, the most densely covered area is the center of the galaxy, of the Milky Way. We also have a bunch of events in the galactic disk, and even some in the area of Magellanic Clouds. As I mentioned before, we can make our work slightly better and the light curves of the microlensing events found in Gaia Science Alerts slightly better through follow-up network. And this is the image of all the facilities that we have worked in the past or that we are currently working. We have worked mostly with LCO, with SMART, SRAM, other facilities, for example, Malatai Observatory or Aristarchos. And in order to gather our data, we use the service that will that you will hopefully know after this workshop, called Black Hole Tom. Also, using this service, we provide this webpage. We provide the list of the most interesting targets for us for microlensing. So if you're interested in following a target, and if you want to join the network and provide some observations, you can use this website and search for a target which is observable for you, and also what is the priority for this target. And this is the image in here. That's the image from the web page with sun and moon located here, and this is the red dots represent all targets which have been registered in Black Hole Tom. So now moving on to some highlights with follow-up from various sources. This is a bunch of events that, almost one per each year, even two, that have been pretty interesting. Some of them I have even analyzed, like for example, Gaia 18 diff. Others have anomalies or are binary events. So this is very interesting, and also pretty exciting is that some of them are not located in the galactic bulge where we observe majority of microlensing events. Last year I talked more, so this year about this event. So this year I just want to show you Gaia 18 CBF was an event that I have analyzed last year. It is the second longest microlensing event in terms of the time span, because the Einstein timescale, which is so like the effective timescale of the event, half time of the event, was over 400 days. And it was also very dim, which meant that we couldn't really use many telescopes for follow-up. But nonetheless, I managed to analyze this event, and the results of this analysis is now, you can read it in the now published article in ANA. Second most exciting thing for me is that I've been finishing my PhD thesis, and while I was writing it, I created a catalog, like a fairly definitive catalog of candidate microlensing events from Gaia Science Alerts, and it collects data from 5 years. I have managed to find over 400 events within this catalog, and I provide both very preliminary models and fairly preliminary classification. This is This is an image of how this catalog looks, basically, but you can find it using this link. Sorry, my cat was moving. Maybe if I have time, I will go to this page, but now I want to move to the next slides. These are the even more highlights from this catalog exactly. As you can see, we have many different events. Some of them are still ongoing, and a lot of them have very interesting data and very interesting flight curves. So to summarize, Gaia publishes microlensing events from the entire Milky Way, and soon with data release for we will have astrometry for those events, at least for the events that occurred during the time span of data release 4. Gaia is capable of finding long events, and also capable of finding events, microlensing events, which are not in the areas which are routinely covered by other microlensing surveys. And there is a new catalog of microlensing events which you can check and use, and maybe, I don't know, use in your research or compare it to your results. And in this place, I would like to thank everyone who is working with us for their support and their ongoing work. on microlensing events. Otherwise, the research that I have been doing wouldn't be possible. So thank you very much, and I will take questions now.
Thank you, Katarzyna. So do we have any questions on Zoom?
Nothing there.
Questions from the audience? Anybody? No? So thank you, Katarzyna, for your talk.
We can't hear you.
Yeah, so sorry, I have a question. I have a moment. Can I show the catalog on the webpage? Would that be okay?
Yes, we still have like almost 10 minutes, so go ahead.
Oh, okay. So no, I maybe use up 5 minutes for that. Okay.
Perfect.
But I'm really excited, and I really want to show it to other people. It's not a definitive work. There will be a paper and at some.
We chat with Lukasz.
Sorry?
Or maybe that's catalog, right?
Catalog
It's
of
very
swear
exciting,
words.
yeah, indeed. It's very clear.
Can you see my screen? Because something.
We see your screen, but with your chat, not with your catalog.
Okay, great. Sorry. Yeah, I just noticed that the wrong screen got shared.
That's why.
Yeah, probably my cat. Yes, exactly. Okay, so now you see probably my desktop. Ah, there it is. So this is my homepage, and this is the link that I provided in my presentation. This is a short description of the catalog, and this is just stuff for my students that I used to teach. So if you click here on this link, catalog in CSV format, you will download a link, a file. Yeah, this looks like this. So that's a CSV file with badly not well visible. Sorry. I'll just open it like this. You have the name of the alert, you have the coordinates in degrees, and then there's the preliminary class. There's several types. One is PSPL, which means like a standard single microlensing event. Bin means binary. There's also par, which means that it could be a parallax event. And if it has question marks, it means I'm not sure. And also I provide in here names of such targets if they occur in other microlensing surveys, for example. Also, if they do appear as a target of interest in Black Hole Tom or an Omega key projects, other key project for LCO service. So there's that too. However, if you want to check the light curves for your favorite events, for example, it's a candidate microlensing event, a binary system. Here remarks that I really want to pay people attention to this because there are many problems with these preliminary results. But once you click on the list, you will get, okay, this got broken. You will get an image with, well, for example, because it's a binary event, the obtained model is not very good, so it gets a little bit crazy. But for example, for this case, you will get a nice table like with names, links to other places on the internet. For example, this is a target also, which was also observed by Howil and published within Howil through Howil EWS. So you can click on it, go to the web page for this alert and check the information provided by this survey. And there's also like a very preliminary model with and without parallax effect. And then there's a little zoom. And these are other preliminary models found through multi-nest algorithm, which has its problems. So I won't go into details for that, but that one, the last one is just for fun. I would focus on the other panels of this plot. And you can also, and there's the similar thing available for standard microlensing events. There are much more of those. Let's go, for example, to the last page. And here I provide the same thing, however, only with standard microlensing model without parallax. And additional comment is that in order to make it easier and slightly more stable, I assume that there is no additional light. I assume the 100% of light is coming from the source in these preliminary models. If you want to have a more detailed analysis, you will have to do it yourself. Okay, so I think that's it about the catalog, and I can stop here. And if you have any questions, you can always catch me on Slack or somewhere. Thank you.
Okay, Kasia, thank you very much for the talk. And this is the end of the first part of the afternoon session. Thank you very much, and let's go for coffee.
Catalog is such a good name in that case.
Okay, thank you. We'll be back in half an hour.
So at all day, right?
No właśnie, wczoraj sypiały,
A dzisiaj się włączają
się
i
wyłączają.
zamieniamy. Wszystko wyłączałam i może odpoczęły nieraz.
No dobrze, dobry pomysł. Tak, no ale to jest nieprzyzwyczajone, kasowe cały dzień tym mikrofonem, kasę.
Ale głoszę, widocznie wiesz, jest tak.
Cisza.
Speaker mówi jeden, a ja coś mówię.
Gdzieś od kamery.
To będę
proszę.
podawać.
A, no.
Albo ci będę przekazywać.
Nie, no tak.
Valerio jest gotowa?
Możesz go wywołać.
Okay. Valerio, are you there?
Yes, I am. Can you hear me?
Yes, we hear you, we see you. Please share the presentation with us.
Can you see my screen?
Yes, we do.
Okay.
Okay. Hello, everybody, after the lunch break. We start with online speaker, Valerio Bozza will be talking about astrometric microlensing phenomenon. Valerio, please start.
Okay, so thank you very much. So this presentation will be about the software. So this VBBinaryLensing is now a widely used tool for the computation in microlensing. So I hope that this presentation will encourage people from the Gaia network to approach microlensing using some of the tools that have been prepared by me, but also by other people in the microlensing community. So many people have already spoken about astrometric microlensing. So you know that in practice in microlensing, the images are unresolved, are not resolved by current facilities unless we use BLTI in one or two cases. And we can only try to observe a centroid shift. So by precision astrometry, we may detect this centroid shift, and here we have some analytical formula about this shift. Now, the good thing about astrometry is that it gives a direct measurement of the Einstein angle. So it gives a very precious additional information, the Einstein angle that characterizes the gravitational lensing phenomenon. Now, astrometric microlensing has been measured in a few cases. It's a very young field in some sense because the first detections amount to arise to about 5 years ago with what was detected, whose astrometric microlensing was detected by HST, for example. Then we have Proxima Centauri, which was predicted to lens some nearby stars, and this has been observed by VLT. And then we have, this year we had this very nice detection of astrometric microlensing, which actually it was for an event in 2011, but it took several years of observations by HST to be confirmed as a candidate black holes by two different groups. And finally, we also have Gaia, of course. So Gaia will provide astrometry for the many microlensing events. And so this is a very preliminary study by Kruszyńska about this exciting event, Gaia 16 AE, which was followed by many groups in the Gaia follow-up network. So there are very many possibilities that are opened by Gaia. And of course, we look forward to the astrometry release from Gaia. Now, looking toward the future, there will be the Roman spacecraft, the Roman mission that will be launched maybe in 2026 or something like that. And this will conduct a dedicated survey to microlensing in the galactic bulge. So with a cadence of 15 minutes, we can expect many detection of microlensing events. But of course, one thing is to observe a photometric microlensing event, but not all these events will give an observable astrometric shift. So in this, if we just plug in a basic galactic model and we try to check how many detections we expect with some given threshold for the Einstein angle, we see that actually the total number of detection is very sensitive to the threshold we put for the Einstein angle. And so going from 3 milliarcseconds to 0.3 milliarcseconds, the number of detections changes by 4 orders of magnitude. So this means that we really have to push the astrometric sensitivity of Roman down to below 2 milliarcseconds if we want to exploit this great potential for astrometry. well, this is just a video showing some simulation of an astrometric shift during microlensing, but this is for an exaggerated 100 milliarc-second event, which is, of course, not possible in reality, but just to see something showing up in the images. Actually, we expect Einstein angles of the order of 1 milliarc-second or so. And the precision of that we expect from Roman is about 1 milliarc-second, but we should not forget that actually we have about 100 observations per day, which means that by combining these observations, we can bring down the statistical uncertainty by about 1 order of magnitude. So in principle, we can go below 1 milliarc-second precision with Roman, but of course we have to keep control of all possible systematics, which is not easy, and we don't know exactly what to expect from this space mission. But anyway, there are very good perspectives for astrometric microlensing in the future, so it is worth investing towards this direction. And because astrometric microlensing gives us this additional information that might be very precious to break the degeneracies in microlensing. In practice, the astrometry can be considered as complementary to the finite source effect, because we can have access to the Einstein angle to the finite source effect, but this is particularly relevant for lenses that are very far from us and very close to the source, while astrometric microlensing is more sensitive in the case of lenses that are nearby, that are close to the observer. And in this regime, actually, we can also have more chances to measure the annual parallax. And of course, the combination can give us a precise mass measurement. In addition to this, we can also combine the measurement of the flux of the lenses, and this gives additional constraints to the mass and the lens. But if we do not observe any flux from the lens because the lens is dark, then astrometry becomes the only way we have to resolve the degeneracies and to have access to the mass of the lens. And that's why this is so interesting for the study of dark remnants and black holes, as we have seen in the last few cases. And of course, this requires a simultaneous modeling of photometry and astrometry. So we need a software that takes care of astrometry in the same way as it does for astrometry, and we have to keep into account all the higher order effects we know from microlensing. For example, the finite source effect, limb darkening, the case of binary or planetary lenses, including all the higher order effects such as parallax, orbital motion, and Salad. And that's why VBBinaryLensing provides a possible solution to this. VBBinaryLensing now is at version 3.4 actually, and it's a microlensing computation tool including advanced methods. It's a public code. We can find it on GitHub. It's written in C++, but it is importable in Python thanks to a Python wrapper basically maintained by Etienne Bachelet, who is collaborating to this project. And now VBBinaryLensing is the core modeling. It's the core computation code used by several platforms for the microlensing modeling and computation, such as Pylima, MuLens Model, and Mulan. So I invite all people who want to approach microlensing to download one of these packages and try to put their hands on microlensing events. And VBBinaryLensing is also adopted as a base computation code in the future pipeline that is going to be developed for the Roman space mission. Just a few technical details about VBBinaryLensing. So it uses a lens inversion algorithm by Kornel and Gold. It is based on contour integration. So the area of the images is calculated by taking points around the contour of the images and by calculating the integral using Green's theorem. Actually, we also include a parabolic correction. So for each arc, actually, we increase the accuracy to by 2 orders in the expansion of in the length of the arcs. And we also have estimators for the error in each boundary arc. So this is, of course, needed if we want to optimize the sampling where it's really needed. So the code includes additional points every time we have a large error in one of the arcs, so that it works in the most efficient possible way. And in order to calculate the limit darkening, we have to repeat the computation on concentric annually. We have also included a decision tree, which is necessary when we have a long microlensing cycle, so that the full calculation is only done only when it's really needed. And higher orders are included in the computation. Concerning astrometry, the calculation of astrometry actually requires two additional integrals, because the centroid, the calculation is basically given by this formula. So in the denominators we have the area, the total area of the images, and then in the numerators we have the position of the image elements weighted by the area of the images. So in practice we have to calculate these two additional integrals. But once we have the contour for the images, we just have to perform these additional integrals, which comes almost for free. So in practice, the code is as fast as with the calculation of photometry only. The parabolic correction is also included, so this gives improved accuracy for the astrometric computation. Now, if we do calculations for the binary lensing, for binary lenses, we know that we have the sudden creation of additional images every time a source crosses a caustic. So here we have the formation of two additional images. The two images are destroyed here when the source goes away from the caustic. And this brings to sudden jumps in the centroid trajectory. Now, if we also include the finite source effect, these sudden bumps are somewhat smoothed out, and this smoothing becomes more and more important if we go to larger and larger sources, of course. Limb darkening is also included in the computation, but actually it gives a very tiny effect on the centroid. So with our current facilities, we don't hope to distinguish between these different trajectories, even for very large sources. But anyway, it's taken into account. For the single lens case, we know that a centroid trajectory is basically a simple ellipse, so it can be calculated analytically. But if we also include the finite source effect, we have a perturbation here in this ellipse. And this can be calculated through elliptic integrals. The best solution that we find is to use pre-calculated tables of these elliptic integrals, which makes the code extremely fast and much faster than any other possible codes. Now, this is just an example of use of VBBinaryLensing. So this is just a piece of code in which we specify some parameters, the separation of the two lenses, for example, the mass ratio, the position of the source radius, and then we turn on the astrometry to true, and we calculate the binary lensing magnification, and of course we can print the magnification and the position of the centroid of the images. So it's very easy to use, and it's fully documented in the files that you can find on the GitHub. Now, additional features that are offered by VBBinaryLensing are the calculation of full light curves for the standard sets of parameters. So for example, in this case, we have the calculation of a static binary lens light curve. And here we just provided the separation, mass ratio, impact parameter, angle, source radius, Einstein time, and T0. And then we can calculate the light curve using this function. And if we also want to include parallax, we also specify two more parameters to the parallax component. Orbital motion is also included. This is for circular orbital motion, which we have to specify three components of the velocity. And but if we want to include the Keplerian orbital motion, of course, this requires two more additional parameters, and we have several parameterization that have been proposed in the literature. Here we have our proposal in which we have added these two parameters here. As an alternative, we can also have the Xalarap effect, which is the orbital motion of the source. And in this case, we have the different parameters here, here that can be included in the calculation of the light curve. And you know, as the accuracy in our photometry and in our astrometry is increased, we have to consider all these possibilities if we model very complex events. So this last slide is about orbital motion. In the microlensing literature, we often find the linear approximation of orbital motion, in which only two components of the orbital motions are specified. Basically, the orbital motion, the component of the velocity along the binary lens axis and the perpendicular to the binary lens axis, but perpendicular to the line of sight. In principle, this linear approximation works fine for the very slow orbital motion, but as soon as we have a long enough event, actually this linear orbital motion, which is this black line here, does not correspond to any real physical orbits because it's just a linear extrapolation. And so the recommendation is to use a circular orbital motion at least, if not a fully Keplerian orbital motion, because otherwise we could get unphysical results. And this was also, this point was also made by other people in another publication. So the conclusion is that, of course, astrometric microlensing is just starting to give the first results with Gaia and with HST and so there are many expectations for the data astrometry release from Gaia and with the Roman space mission. And in principle, we can get a mass measurement for hundreds of dark lenses, which can give us the possibility to have statistics of the population of black holes and other dark remnants. In this respect, the VBBinaryLensing has become the reference code for photometric and astrometric microlensing. You can find it on this GitHub page, and these are some publications about explaining the details of this software. And the software offers a very wide range of possible uses, from very basic calculations to advanced functions. So I hope we will enjoy playing with this code. So that's all.
Thank you very much, Valerio, for your talk. Are there any questions on Zoom?
I don't see any.
Okay, none. And from the audience? Anybody? Okay, Lukasz had.
Hi, Valerio, this is Lukasz here. And so you've mentioned the Gaia 16 AYE, and this is just actually a comment. So the astrometric solution found by Kruszyński was actually done using, if it wasn't the VBB available those couple of years ago, then that would not have been possible at all. So because the problem here was that we knew the photometric model fairly well, and it was extremely complex. It was a rotating binary and doing crazy things while lensing. And so what Chris did, he actually, it made his life much simpler because of the availability of VBB. So I wanted to emphasize your contribution to that.
Okay, thank you very much for pointing to that.
Thank you. Our next speaker is Zofia Kaczmarek. She will talk about 1D astronometry and microlensing.
Second. Wait. Yes, and now.
All right.
Wait.
This work?
Yeah.
Wait. Not yet. Now.
Hello, everyone. My name is Zofia Kaczmarek. This is actually the second day of my PhD at the MPIA in Heidelberg. So you can see I'm having a very nice start. But today I'm going to talk about some work I've done during my master's in Cambridge. So first I'll I'll tell you what's the motivation for this talk. So as Lukasz said, Gaia provides data in photometry, spectroscopy, and astrometry. And we've had a great deal of talks about photometry. And as you can see, Gaia alerts and photometry are, the database is increasing every day, and we're having more and more events. We've had some talks about spectroscopy, where the variability change in the object in time is seen in the spectrum. But so far, we haven't heard about Gaia data, Gaia astrometric data, providing some information about the transients. And so far, from the previous talk, we already know it's possible. There are some transients that are also astrometric transients. There's astrometric microlensing. So why this empty space here? Do we have any events that could fill this space? I won't spoil for now, but I'll just tell you the reason why it's not as widely covered. There are actually two reasons. So first of all, this is on the very limit of our detectability. This is on the very limit of our technical possibilities. And the second reason is that Gaia astrometric data is actually a little bit complicated. So I will first give you a quick reminder or introduction on how Gaia provides its astrometry. So Gaia scans the entire sky following a very unique observing pattern called the scanning lobe, that you can see here, colored by frequency. So for example, you can see it avoids the galactic plane. And the characteristic thing in here is that there is a huge difference in errors along the direction of the scan and across the direction of the scan. These errors are so different, as you can see here, that practically only one of those dimensions is useful. So here you can see the same image, but spoilers. Here you can see the same image that's colored by angle. So each point of the sky has the Gaia scan, and it's colored by where Gaia is looking at the moment. And if it looks complicated for you, a metaphor I really like is that our celestial globe, the map of the sky, is a ball of yarn. There's a ball of yarn wrapped around the whole sky, and Gaia is a kitten that's playing with this yarn. And what it's doing is untangle, 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 untangle. Oh, I see a star here. So it's following this 1D thread, and because Gaia is a smart kitten, and because we know exactly the pattern in advance, it can provide information about where this star is just found lies in the sky. And by revisiting the star, by revisiting it from different angles, it can see how the position changes in time. So from this easily readable 2D map, what we actually have in Gaia is this on the right. So we have just the deviation along the scan direction. But that's not the only way this data is tangled. That's not the only way it's complicated. For now, we can't even see this part. We can't even see the time series astrometry. What we have is the part on the right. So how Gaia fits a simple 5-parameter motion to this 1D data. So the 5-parameter motion is just position on the sky, the proper motion that follows a straight line, and the deviation from this straight line, that comes from the parallax effect. But of course, not all stars will follow this simple pattern. By the way, if you were wondering why for every observation point we have those groups of dots instead of one dot, this is also a consequence of how Gaia is made and designed. And every time a star passes the Gaia focal plane, it visits nine Ccds or 8, depending whether the row is obscured by this little part that's for realigning the telescope and making sure it follows this scanning low pattern. This is how it looks in the diagram. This below you can see how it looks really on the spacecraft. So just an explanation for how this plot looks like. the point is we have those results on the right. So if you look closely, those are just the 5 parameters, position, 2 components of the position, 2 components of the proper motion, and the parallax. A few correlations between those parameters, and some statistical measures of how good the fit is. Can we actually infer from this some information about what's on the very left, about whether there is some astrometric deviation? Well, one way to do it would be to look between Gaia data releases, and for example, say that in the first year of observing, and for example in DR2, Gaia has measured a drastically different proper motion than in the entire mission. So there was some kind of a sharp turn. And this is something that's very useful, for example, in binaries, and would be useful also in astrometric microlensing if we had an event that was to last for a few years. But most of them are way more subtle, way shorter. And how we can use astrometry is now a bit tricky, because basically we're looking at how bad the observations are, and if the observations are bad, we are happy. So a parameter that's much more useful than a proper motion anomaly is the error, the unit weight error. That's actually a measure of how much what we have in the real Gaia time series data doesn't fit the 5 parameter solution. So here on the left, we have a typical single star that follows it very well. On the right, we have some astrometric lensing that increases the unit weight error. What the unit weight error or the UV or the RUV really is just a chi-square statistic that's corrected for the number of observations and for the sensitivity of Gaia per magnitude and per color of the source we are observing. All of this, of course, is not real Gaia data, because real Gaia data is not available yet. If it was available, it wouldn't be 2D. All this exists because of amazing effort from Zofia, who has made a lightweight code for simulating astrometric tracks for single stars, binary systems, and lensing events. It's called AstrometPy. That I'm very happy to have contributed to also. And it is publicly available. You can read the documentation here. If you want to use it for microlensing purposes, now because this is a workshop, I'm having a bit of a more technical slide. So if you want to get started in the repository, you can find a few demonstration notebooks. And in fact, the lensing demonstration notebook is exactly what's been used to generate those figures you've seen a bit ago. If you wanted your plots to be in sync with where Gaia is really looking in the sky and at which angle at a given point in time, you can either get the scanning load package, this is the more Python integrable way, or you can look into the Gaia observation forecast tool. This is a tiny bit more complicated, but it is more accurate and more up to date. So if you need some help with setting this up, you can talk to me, or you can talk to Maja, who is also using this for lensing events. What I wanted to mention is that it has flexible ways to set up lensing events. You can either define the motion of the source and the lens separately, or you can use the microlensing friendly parameters. So what you use for modeling the photometric light curve, U0, T0, and so on. Just a small remark I wanted to make, because I know that microlensing parameters are sometimes defined in different ways. I wanted to make it clear that the U0 we are using, the parameters we're using are heliocentric, and the U0 is the impact parameter from the straight line motion. But this is just a technicality, not to introduce any errors in your possible simulations. Anyway, again, feel free to ask us about anything if you would like to start using it for your lensing events or for your for other astrometric, for example, binaries or any purpose you like to. I would like now to show quickly a few applications of what it can be useful for. So first of all, and the most spectacular application is you can use it for the lenses that have already been detected photometrically, and look how Gaia astrometry can help in constraining their parameters and even breaking the degeneracy that you have if you only model the photometry. So it's a very simple approach that we are using is we have photometric parameters available from the light curve. We inject some additional astrometric parameters, and we see whether this pipeline that closely replicates the Gaia pattern of observation and the way Gaia is fitting reproduces what we see in Gaia data in the fit. So I went through it very quickly, more details, and an actual case of the first Gaia astrometric transient will be shown in Maja's talk. That's right after mine. So I recommend this. But there are some other more loose ideas that I've had that I think Gaia would be useful for. One of them is looking at the very famous now intermediate mass black holes. So objects of masses like those found in gravitational wave experiments. And an interesting thing there is that because those events would be so long, that the lenses are so massive, the Einstein radii are so big, so the events are so long, the changes in the light curve would not be that drastic. So if you look at the light curves below, so the entire span is 1 magnitude. So those would probably not be your favorite or most thrilling Gaia alerts, if they would be alerts at all. But you can see that they are actually visible. There is some excess noise in the Gaia fits. So, and Gaia would be most sensitive to the order of magnitude that would be tens of masses. So those are transients that would be even more astrometric transients than photometric transients. Astrometry alone could be a way to find this kind of transients. Just the last thing I wanted to mention is that something that is very straightforward to do for Astromet, as it was primarily designed to handle binary stars, is to simulate lensing events that have binary sources. So we know that a lot of stars are in binaries, but when we usually model microlensing events, we usually assume that the source is point source. But often we have little deviations from the point source point lens model that we can't really explain. And even in the detection of the first astrometric microlensing black hole that was mentioned before, there were some discrepancies that were suggested that perhaps binarity could explain it. So this is a problem that still needs a lot of looking into. And something I am really curious about and would like to look into in the future is whether Gaia, not at this stage, but at the stage of the actual time series, could tell us something about the binarity of the source, whether adding astrometry would help. So those are just examples. We came up with more use cases, and I hope that someone will use it and someone will even invent even more use cases. Now, at the end, I will just show a small teaser of what's coming after Gaia with the Roman Space Telescope. So a small exercise I did this year was simulating one of the lenses found in another project as it would be seen by the Roman Space Telescope. So Roman will have 2D data, will have way higher precision than Gaia of an order of 1 millisecond. However, Gaia will still be unbeaten in the whole sky because in Roman Space Telescope we will be just limited to the galactic bulge. But why am I showing this? Why is it even relevant? So in this experiment, we were able to break the degeneracy and recover the lens mass really, really precisely. But with this amount of data and with the 15-minute cadence that is coming with Roman, it was a really huge computational challenge. And I've also had this. We've also had this idea that we could apply some lessons learned in Gaia to the future Roman database, and we could again look for purely astrometric transients by just applying a simple 5-parameter fit and looking for objects that deviate from it. And this way, we could detect interesting objects that could have then their masses measured to an unprecedented precision. So this is all I wanted to present today. Some take-home messages are that Gaia is a very precise astrometric mission. Its data format is very unique, but it's not something to be scared of. It can be very helpful for lensing events, especially. For now, everything we have are the fits. We don't have time series data yet, but one man's trash is another man's treasure. So the fits that would be the objects that would be rejected in constructing a lot of databases because they have high unit weight errors are actually what we are looking for, because those errors could, of course, not always, but could in some cases indicate there's something more hiding in there that is an astrophysical phenomenon, such as astrometric lensing. Astrometry can serve both as a degeneracy breaker for photometric lensing events, as something that will let us finally measure those masses we are running after. But also it could be, and it will be when we are moving towards more precise data, an indicator of lensing on its own. And Roman will go much further than Gaia, but Gaia will still remain, for now, the only mission that's scanning the entire sky and, for example, let us probe the galactic halo. So it's, I think, important to focus on both and focus on all the data we have available. But the most important take-home message would be that it is an incredibly exciting time for astrometric microlensing. And feel free to use the codes for all of your needs. So I'm linking to the Astromet software. I'm also linking to the package I have used to simulate the Raman observations. And if you have any ideas, suggestions, bug fixes, pictures of cute kittens, or anything, you can contact me on my email or on the workshop Slack or at coffee. Thank you very much once again.
Thank you. It seems that afternoon session is ruled by cats. So do we have any questions on Zoom? And here, Simon, please.
What is the duration of the Raman mission compared to the length of the massive black holes, intermediate black holes that you're looking for? Are they comparable?
So the Raman space mission will have a kind of a tricky observing pattern. So with Gaia, we have a cadence of like tens of days, but it's distributed more or less evenly. With Raman, we'll have 3 periods that are very well covered with this 15-minute cadence that will be separated by half a year. Then there will be a break, I think, of an order of 1.5 years or something. But like the order of magnitude is years, and then there will be also 3 consecutive seasons. So it is still quite small compared to the duration of a microlensing event, but I think the only thing we need to see, we don't need to see the entire microlensing curve. We just need to see that the path that this object is following, the light source is following, is curved over a long period of time in a way that we can't explain with just a 5-parameter field. So actually, we don't need to see the entire for that, the entire duration of the event for that. And also, when we're having such cadence, even the gaps between them don't pose a huge problem because the errors we're having are really small.
Thank you very much. Anyone else? No, thank you.
Thank you very much.
So our next speaker is Maja Jabłońska with the hidden lenses.
Hello. Okay.
Thank you. My name is Maja Jabłońska. I am a PhD student, and I will be talking about the results of my master's thesis. So using Zofia's code to actually find a microlensing source hiding in Gaia DR3 astrometry. So first I will present the source briefly, then I will explain why isn't it straightforward, and review that a bit with the probability of it being dark lens. Oops. Sorry. Yes. So I don't have to introduce Gaia mission, but what's important here is that Gaia produces the 5-parameter solution when analyzing the astrometric track. So we receive coordinates, proper motion, and parallax. Normally we can trust these values, but not when something else is happening in the source, because it is assumed that the source is single and the only motion is parallactic. So whenever we have an unresolved binary or microlensing, this solution isn't correct because it's not a single parallactic movement. And Gaia ULens 001 is an example of such a source that it appears that something else is happening, because as you can see, the Ruve is over 218, and normally, as far as I know, the threshold of acceptable solution is 1,4. So definitely something is going on, and luckily, luckily we also have photometry, and on the photometry we can see that we have quite well-known shape, so it's reasonable to assume that it is microlensing what's causing this disturbance. So I have fitted the microlensing photometric model as usual. Just a second. Yes. Following the same techniques as all my colleagues from Warsaw do. And received this, since there is a parallax detectable, this event was long enough, I have received these 5 values with B being a vector. So quite a standard procedure. But of course we still have, there is no binarity, no finite source effect, so we are missing, this there is a degeneracy of lens distance, theta e, so Einstein radius, and the relative motion of lens and source. So we decided to take these parameters inferred from the photometric model and add them to the known 5-parameter solution, which was actually produced from the astrometric track, and we can see it's not correct. So there is an additional movement there. So this was my procedure. I have added the guesses of the 3 degenerated values, added the values assumed from the photometric model with some scatter, because of course they were modeled as they were inferred as well, so they had their own errors. But the source is quite bright. It was around 13 magnitude, so this model was quite well defined. And this may seem a bit cryptic, I will explain that in a minute, but there are measurement errors that were fit as well. And I have used Astromet, that was presented just a while ago. I have run that on GPU because I needed a lot of samples, and I have fitted the 5-parameter fit. So fitting the fit was quite a convoluted procedure, but it appears to be working. And what about these errors? So as you can see, when calculating the Ruve, we use the chi-squared. Chi-squared includes information about the individual per CCD measurement errors. And we don't really know what these errors were, but this is a bit important. We cannot really neglect that because they influence the Ruve calculation, and there is a function which, using this function, we can infer the AL measurement error expected for some magnitudes. So I have taken all the magnitudes, of course, including the brightening, and then summed all of these to obtain the expected measurement error sum, because it's the sum that enters the equation. And then what was important was to fit an additional parameter, I call that a scaling parameter, to the sum of the errors to actually fit the obtained errors. I think this is the most convoluted part of this whole process, but it was important because, as you can see, the inferred Einstein radius depends on the actual measurement error, and therefore it had to be fitted. And as you can see, the blue clouds of solutions are the simulated solutions that fell in the range of consecutive 3 to 1 sigmas of Gaia DR3 solution. The black one is the one that had the Ruve in some acceptable range, and I have calculated this acceptable range by bootstrapping the values, since we had some additional uncertainty introduced by the photometric model, and then fitting the actual errors. The per CCD, per astrometric measurement error influenced the errors inferred, the 5-parameter errors, and these were fit as well. And having this fit, this 6-parameter of the source movement, the source proper motion, source distance, the theta parameter, and this scaling parameter, one could obtain the lens mass, the lens distance, and here is the result. Unfortunately, or maybe not unfortunately, but surprisingly, I have also this resulted also in 2 solutions with negative and positive U0, and it wasn't clear to me, will it be like with the photometry, that the 2 solutions will appear as well, but they didn't converge. So they were quite similar, but I'm presenting just one for clarity. So the lens is around 1 solar mass and around 1 kiloparsec away. It's quite nearby. This is the simulation of the best solution, the closest one of its track on the sky, and some random sample of tracks just to illustrate how this differed for different parameters. These are the results for the 2 solutions, as I have mentioned. They're quite close, but they correspond to a bit different scenarios. And what about this darkness that is in the title? So this lens is quite nearby, but the photometric fitting indicated that the blending parameter is quite high, so probably the lens light is very insignificant. And 1 kiloparsec away, we can estimate what is the possibility of a main sequence star being there and not being seen by us. So the lens is, of course, the source is very bright, so it can swallow the lens light, but still it's just 1 kiloparsec away. And the dark lens, which was used also by my other colleagues in Warsaw, indicated that it is rather likely that this lens is dark. So this event is not in the bound, the extinction is very small, and as you can see, it's at least 75% of chance that this is a dark lens. So to summarize, we have a dark lens around 1 solar mass, and the most obvious choice is probably a white dwarf. I have compared that to a DR3 catalog of white dwarfs, which is very new. and the positive U0 solution corresponds to some larger white dwarf, and the negative solution corresponds to some average white dwarf. What needs to be said here is that unfortunately we cannot really rule out the possibility that this is an unresolved binary. So I think this has to be explored in the future to just estimate what kind of a binary could that be, because these can be two red dwarfs that are really, really small. But still, the suspicion that this is a white dwarf, which is quite nearby and quite massive, is it has its grounds. So this is the result of my fitting. It has all been done using the great work of Zofia and Zephyr and their team. And we are going to continue this work of fitting astrometry, but the next time we are going to do that is to do it with time series, because this is the new level of powerful data, because we don't have these problems with fitting the errors, which sounds a bit strange, but it's necessary. And I believe we are going to find a lot of treasures there. So yes, to summarize, Gaia DR3 data is awesome. It has a great precision of astrometry, but Gaia hasn't released the time series yet, the astrometric time series. So we have to wait for that. But I believe we are going to do that with Deepak. When the time series are going to be released, this is going to be a mine of various phenomena. So having no access to the time series, I have done everything to squeeze out all the possible information from the 5-parameter fit. With MCMC run on GPU and optimizing a lot of things. And I have inferred some estimate of lens mass, which is not that broad to be unable to estimate what kind of object is that. And most probably it's a nearby isolated white dwarf. Of course, other scenarios cannot be ruled out. And of course, apart from time series, another step that could be taken, and probably would be to analyze the spectra, because we might expect some UV excess, which could indicate the white dwarf scenario. And I would like to dedicate this talk to the white cat. I think he or she lives in this hotel and is very cute. And thank you very much for your attention. I'm very happy to talk about everything, and it will be published very soon as a letter. It's like at the end of the correction process, language correction, and here's a link to this work. Thank you very much.
Thank you, Maja, very much. Congratulations on the letter. And wonderful catching.
Thank you.
Questions from Zoom?
No.
Okay. And from the audience, Mariusz?
So it's not clear for me why you exclude the mine sequence when solar masses start.
Well, I don't exclude it. It's just that the possibility is not that large. Of course, it's a viable scenario. It's just less possible than the dark lens scenario.
Yeah, but this is quite easy to exclude or not exclude, because you have the given brightness of the stars. This is mine sequence, and you can easily predict. And it is to find the microlensing event in the max or in the baseline to exclude that.
Well, I mean, the probability was calculated using dark lens. So these are the probabilities of mass of main sequence at this distance with this brightness corresponding to the fitted blending parameters. So Yes, as you can see, the main sequence part is really sparse, but also mind you that this event was really bright. It was 13 magnitude, so you can see that the blend light could, for example, be 16 magnitudes theoretically. Like,
what's in the baseline?
In the baseline, I believe it's 13 something. Let's see. This is the baseline of Gaia G.
So you expect like 15 for the solar mass at 1K?
Excuse me?
Yeah, you expect about magnitude 15 for the sun at the distance of the 1 kiloparsec.
Yes.
Okay, thank you. Anybody else?
I have a
Okay, Lukasz?
just a comment that with this event, what we could think of doing is some follow-up observations. Because this event happened, you see the date. Of course, I'm sure everyone can convert it to years with no problem. This is something like 2015. So this has been already 7 years ago, we haven't measured the proper motion, but we have some idea on the proper motion.
Well, yeah, the proper motion is large enough for it to. It is worth a shot measuring it.
So yes, so after 7 years, we can see the lens and the source separate with some high-resolution imager. And if we do it, for example, in ultraviolet, then the contrast between the source and the lens might be in favor if this is a white dwarf, right? So we might actually see the white dwarf and confirm this theory. But if we don't, then it actually boosts the probability for our main sequence. Microphone. For Carolina.
Not exactly what if it's the old white dwarf with temperature like 6,000 kelvins. So you will not see the X-ray. Or UV.
I'm not saying X-rays, I'm saying ultraviolet. But how many, we talked about it already. So how many old white dwarfs there are? So, okay, but this can be
millions of them.
Millions.
Why you expect that white dwarfs not appear?
Then we will go for JWST and then we see it.
Okay. Thank you very much. Thank you, Maja, again.
Thank you.
So our next speaker is Somayeh Khakpash, and I hope I didn't make an error with the name. Do you hear us?
Yes. Can you hear me?
Yes, we hear you, we see you. She will be talking about microlensing from the point of view of Vera Rubin Observatory. So we waiting.
All right. So I'm now going to put this. Can you see my screen?
Yes.
Okay. All right. Let me just. So thank you so much. My name is Somayeh Khakpash. I'm LSST Catalyst Fellow at Rutgers University. I'm also the coordinator of the Rubin LSST TVS Microlensing subgroup. I'm really happy to be here. I hope I could be there in person. Unfortunately, it was impossible. And thank you for the invitation. In this talk, I will mainly focus on the type of microlensing science that we're thinking to do with Rubin LSST and the kind of activities that we're doing to be prepared for that. But before that, I will use this chance to give you an overview of the current status of the project. All right. So in this talk, I will talk about first the Vera Rubin Legacy Survey of Space and Time, LSST, and then I will talk about the kind of like microlensing science we want to do, and then at the same time talking about the sort of activity we do within the microlensing subgroup of the Transients and Variable Stars Science Collaboration, in short TVS. So as many of you probably know, Vera C. Rubin Observatory is going to conduct a 10-year legacy survey of space and time, LSST. So Rubin Observatory is doing the survey, which is the LSST. And in short, we say Rubin LSST or Rubin itself. And it it's going to be an 8.4 meter telescope. It's being constructed in Chile, and it's going to observe the whole southern sky, pursuing 4 main scientific goals: probing the dark energy and dark matter, taking an inventory of the solar system, exploring the transient optical sky, and mapping the Milky Way. So in this slide, I'm summarizing the anticipated SAVOR operation timeline, the most updated one. And I have made it into different stages depending on the sort of data releases. So it starts with DP0 data preview 0.1 and 0.2, which are basically simulated LSST-like images and catalogs from the Dark Energy Science Collaborations Data Challenge 2. And these are currently available to DP0 delegates, people within the community who registered for an account. And the next one is DP1 data preview 1, which is based on the commissioning camera. This is a camera that is going to be installed before the actual SST camera, and it's going to make some observations to do the calibration. And the data for that is anticipated to be released between March 2024 and July 2024. And the next one is data preview 2, which is actually going to be based on the LSST camera data sometime between December 24 and March 25. And then finally, data release 1, which is based on the first 6 months of the LSST data, which is anticipated to release sometime between October 25 and January 26. So the first light with LSST camera is now anticipated to be sometime close to February 14th, 2024, the Valentine's Day. And so I will here shortly talk about the data products and the distribution of the data products. So the images taken by LSST, the raw images that cover the entire visible sky every few days, that accounts for about 20 terabytes of data per night. The raw data from that, 2 sets of prompt data products and data release products will be created. The prompt data products include the alerts, which are basically alert packages for each object containing information about the observations for that object, which will be released within 60 seconds, and it will be released to the community brokers. And the brokers are basically algorithms that are developed by the community, and they're responsible for receiving the alerts and analyzing them and classifying them and making them prepare them for being released to the community. And the alerts are public to the whole astronomical community around the world. The other types of data, prompt data products, including the DIA, different image analysis, solar system objects, and the data releases, which are going to happen annually. Those are accessible to astronomers in the US, in Chile, and the international community that holds data rights. And the Rubin survey strategy is not finalized yet. The baseline survey strategy that was first introduced for the project, for the survey, it was designed to meet the basic requirements to achieve the 4 main goals of LSST. And it includes the main part is the wide, fast, deep survey, which is pretty much most of the area within the survey, footprint of at least 18,000 square degrees, an average of 825 visits per field over 10 years. There are the deep drilling fields. I can see the yellow spots. Those are single pointings, which will be observed with a much higher cadence. And then there are the mini surveys, which cover smaller area of the sky compared to the wide, vast, deep. And they are focused on different like particular science cases, and they're being observed with lower cadence. And so in order to actually optimize this survey strategy, the Rubin LSST scheduler team, they are generating a wide variety of simulated surveys, which are called the operation simulations, or in short, OPSIMs. The OPSIMs consist of the input, which is the strategy parameters like the area, number of visits, and they generate 10 years of moon cycles, weather patterns, and they also simulate the schedule for 10 years of observations. And then the output is a database, including all the observational metadata that people can use to evaluate different questions. So, and they also have developed the metric analysis framework, or MAF, which is a code package within which scientists can write pieces of codes named metrics to evaluate the different survey strategies. So this is a framework that is that has been used by the astronomers within the community. People with different scientific goals, they write different metrics, different pieces of codes within MAF to evaluate the different survey strategies and show how effective each of those survey strategies are for their science cases. And that comes to what part of the work that the different science collaborations of Rubin LSST have been working on. So I'm showing this this is a slide here to basically like show like the different science collaborations. But what we have been working as a part of the transients and variable star science collaboration in the microlensing subgroup. So with that, I will move on to talking about microlensing. So today we have heard a lot about microlensing, so I don't think I really need to go through a lot of introduction. We already know a lot about it. So I will just show this picture here. These are simulated light curves for like high cadence survey, nominally Roman here. But what I want to show is like the sort of light curves that in a microlensing survey you can you might have to deal with, like depending on what sort of lensing system you have and the different parameters of the system. The sort of like perturbation, the shapes that you might see in the light curves. So why are we talking about Rubin in particular? We're talking about Rubin because of its because of the features that a lot of other science cases are also interested in. A large field of view, very deep observations, and the long baseline. So with having microlensing events in mind, Rubin can help us estimate the microlensing optical depth. It can help us find populations of stars, planets, and black holes in the Milky Way galaxy and in the large and small Magellanic Clouds. And we're also interested in the possible synergies of Rubin with other surveys like Roman. So the TVS microlensing subgroup has been working extensively on preparing for microlensing science with Rubin since 2018. In 2018 we released white papers that in which we made recommendations regarding the survey strategy. For instance, we recommended that the galactic plane, bulge, and Magellanic Clouds be covered as part of the wide first deep survey with a cadence of 2 to 3 days, but with a reduced filter set. And we also recommended to have a deep drilling field on Roman's footprint to take observations. And having these recommendations in mind, we have been written different metrics, as I mentioned before, different pieces of code to evaluate different survey strategies. These metrics were focused on evaluating the detection and characterization of microlensing events, evaluating the footprint in different surveys, and then evaluating the possibilities of synergies between Roman and Rubin. So here I want to just briefly mention some of the really great work that the people within the microlensing subgroup and the TVS science collaboration as a whole has been doing. So for instance, there has been extensive work being done on evaluating the footprint of the different survey strategies. This is a work led by Rachel Street, and the idea is to basically look at the different parts of the galactic plane and prioritize different part of the galactic plane depending on what sort of science within the whole TVS science collaboration people are looking for, and provide some different sets of footprint for the math team to basically see if any of those can be incorporated in the final survey strategy. So here you can see 3 different sets of footprints, like very small, medium size, and very large footprint, including the galactic plane and the Magellanic Clouds. These are the areas where not just microlensing, but other science cases, including variable stars, are very important. And there's also the microlensing metric that is now widely used to evaluate the different survey strategies within the Rubin survey strategy team. And so this is the way the microlensing metric works is that there are some input light curves that are input into the metric. For example, 10,000 simulated microlensing events that are distributed across the sky according to some galactic model. So here there's an instance that is that shows the light curves are distributed according to the star density in that region. And then the number of the detected microlensing events are evaluated for different survey strategies that you can see down here, and to see which one of the survey strategies we can say that absolutely not good for our science case. The microlensing metric is now, it has more pieces to it. So it just, it has a detection part in which the fraction of events with 3 points on the rising part with at least 3 sigma difference in all bands is considered a detection. And then it has 2 characterization parts. One looks for a fraction of events with at least 10 data points detected within 1 Einstein timescale. And there's another characterization criteria, which is a fraction of events with a fractional uncertainty of the Einstein timescale of less than 0.1. So this is a work mainly led by Natasha Abrams and Marcus Hundermark and the rest of the microlensing subgroup. And we have used this metric to evaluate the most recent survey strategies that were released by the Rubin team. And what we find is that, so this plot here shows the results of the different metrics here on the y-axis, and you can see the different metrics on the x-axis. The points that I want to focus on are these 2 metrics here that show they did basically the metrics that you see they did not really work well for the microlensing science. And these are basically the older survey strategy simulations. The newest one, the newest baseline 2.0 here, seems to work about like 50 to 60% better than the older survey strategy simulations. And this has been the results of the feedback that the microlensing subgroup has given to the project team about what sort of criteria we're looking for in order for the Rubin to be helping the microlensing science. And I have also zoomed in on that part when I was talking about, so these 2 represent the older baselines. And here we see the newer baselines, and we have different components of the microlensing metric, the characterization, which is the fraction of events with uncertainty, fractional uncertainty less than 0.1, and the total detected events here. And we see that both components of these metrics are improved for the time scales of 30 to 90. For longer events, we find that most of the survey strategies are working basically the same for the longer events. But what we also find is that we do not want like survey strategies where there are like large gaps of like about 1 year happening in a light curve, which would basically be too bad for estimating parallax, for example, on the longer microlensing events. May I ask how much more time I have?
About 10 minutes maximum.
Okay, 10 minutes, sure. So the question, how many events are expected? So back in 2019, this paper was released by Sajjadian and Polsky, and with using the older simulations back in 2018, they did an extensive simulation, and they found that they expect that about 14,000 events will be found by LSST for the whole survey time using the older baselines. And we have not repeated the simulation for the most recent survey strategies, but what we find is that how much the criteria that we have are improved compared to the older baselines, and we can make estimations of how many more events we can find with that. And one other aspect of Rubin that we're very interested in is its synergy with Roman. So Roman is NASA's mission expected to be launched mid-2020s, and the survey, the microlensing survey, will take place during 6 72-day long seasons spread throughout the mission time. It is estimated to find about 54,000 microlensing events and discover about 1,400 planets. So what is the synergy between Roman and Rubin? What aspect of that are we thinking about? Rubin can cover interseasonal gaps of Roman. I will explain a little bit more why that is useful. And Rubin can also do simultaneous observations of the Roman footprint, which can provide microlensing parallax measurements. So with the microlensing parallax, which is probably also mentioned in the talks today, Rubin and Roman with a distance of 0.01 AU, they're going to see a single microlensing event from a different perspective, providing an opportunity for measuring parallaxes on events with a much shorter time scale. So this is particularly useful for measuring parallaxes of free floating planets that Roman is expected to find. And then finally, if we have events, for example, wide orbit planets, where we find that the anomaly is detected by Roman, but the main event, for example, is not. Having Rubin observe the interseasonal gaps of Roman can help constrain a lot of the events discovered by Roman. And within the microlensing subgroup, two of our colleagues, Annibal Varela and Martin Meckler, they are working on doing simulations for Roman-Rubin synergy. They are doing simulations with high cadence observations of Roman, and then doing simulations for for nominal survey strategy of Rubin, and combining those. The question that we're asking is, what can we learn from the precursor data from Rubin, and how much that would be helpful in detecting and characterizing microlensing events. So what they do is that they use the OPSIM simulation, the time steps from the OPSIM simulations, and the trilegal galactic model and the microlens and the Pylyma microlensing model to basically simulate Raman and Rubin light curves, as you can see here. And then they're also the next step is to use these light curves as input to the classifiers that already exist to evaluate the performance, having the additional Rubin precursor data, and see how that improves the classification results for the Raman light curves. And with that, I end my talk here, and I can take questions.
Thank you very much for your talk. First, I will ask audience, do you have questions, comments? Lukasz, do we have Zoom questions?
No.
Okay, not this time. Okay, so thank you very much for your talk. We're looking forward for the Rubin Observatory and hope to see amazing results soon. Or maybe a little bit later soon, but let's hope it ends well. And the last talk of our today's session is Rachel Street talking about developing tools. Rachel, do you hear us?
Yes.
I hear you. Can you hear me?
Yes, we hear you. We see you. Hello. So you can start.
Okay, perfect. Thank you very much. Let me share my screen here. Okay, hopefully you can see my slides.
Yes.
Great. Okay, well, hello everybody, and thank you very much for this opportunity to speak. I'd like to give you an update about some recent developments we've been making to the TOM toolkit, and in particular, some related services that we're developing to help the community to coordinate our response to alerts from Gaia and from other surveys. As always, I'd like to start by recognizing that everything I'm going to talk about is, of course, a team effort, and I'd like to acknowledge the contributions from my colleagues at LCO. So where Gaia and other time domain surveys like OGLE have paved the way, it's increasingly common now for surveys to produce real-time alerts, not just from traditional telescopes, but also now from gravitational wave and neutrino detectors as well. As the LIGO Virgo Cagra detectors don't run all the time, the pressure is particularly high during their periods of operation to really respond effectively to their discoveries. At the same time, the rate of alerts, as we know, is expected to increase by an order of magnitude over the next few years, particularly as Rubin Observatory comes into operation. So that facility, as we just heard, is expected to produce 10 million alerts per night. So the tools that we're developing for this need to be highly scalable to meet that data rate. So these survey facilities have, of course, opened up huge new areas of parameter space. And this week we've been hearing about many of the discoveries, from supernovae to microlensing to TDEs and AGN. But it's also meant that it's become increasingly important to combine different sources of information in real time. This graphic illustrates just one example. It shows the various observational signatures from a neutron star merger that manifest on different timescales. And all of those signals represent data provided by different facilities, both ground and space-based. And we need to effectively combine those data rates, the data streams, rapidly in real time to characterize the targets and select them out effectively. So earlier we heard a talk from Maja and Przemek about the excellent black hole TOM, which is a great example of a target and observation manager system. These are very powerful database-driven systems that allow a research team to manage every aspect of a science program, including the storing of information on data on their targets and their data products, as well as interfacing with essential services such as requesting observations at telescopes, getting data from alert brokers or data archives. This graphic shows an example of a different TOM from the Global Supernova Project, which serves over 100 project members around the world. That was also built with the TOM Toolkit package and customized for that particular science case. So while these systems are very powerful, the technologies change constantly, and there's been a lot of development in the services that they need to interface with to be effective. So I'd like to give you an update on some recent changes we're making to the toolkit. Since the 04 LIGO Virgo Kagra run is in the near future, I'm going to use multi-messenger science as an example throughout, but the planned upgrades will benefit users from all areas of astrophysics. So not all surveys have Gaia's spatial resolution, and the target localization indicated in the initial discovery data may cover a large region. For example, this animation shows the localization of a gravitational wave detection of the neutron star merger 170817. This was very important to identify any electromagnetic counterpart to a gravitational wave or neutrino detection, as it helps us to characterize the origin of the signal. By combining data from several different wide-angle surveys in real time, we can narrow down the area that we need to search for the counterpart. But even if we assume the object is likely to be associated with a known galaxy, we're still left with a very large number of candidate targets to follow up. Any electromagnetic counterpart signal will fade within hours, so coordinating a rapid and efficient follow-up response is essential. And the need to address these challenges is urgent, since the next 04 run is due to start in March 2023. So this will be a very familiar situation for alert follow-ups observers. Surveys already discover more alert discoveries per day than we have resources to follow up. And the situation's only getting worse as new survey facilities become more sensitive and deliver more targets, but also push to fainter magnitudes. This forces follow-up teams to pick and choose in real time which targets they want to follow. And realistically, it's common in many fields that a number of competing teams are going to be following similar sets of targets for overlapping science goals. Although each of the team will have their own algorithm for choosing targets, because they have similar science goals, their priorities are often very similar. And this often means that while some targets receive a great deal of attention from multiple teams, other targets tend to get overlooked. And that's particularly true if they're fainter, since time on the larger aperture facilities is quite limited. That's obviously a very inefficient scenario, since we're missing a lot of science in the neglected alerts. And on the other side, observatories receive competing requests to make duplicated observations of the same few targets. And that's something that a number of observatory operators have expressed concern about. How should they handle these competing requests when the number of alerts rises dramatically? So the focus has been on tools to help observers to coordinate their efforts. So with this in mind, the TOM team have been working on tools to enable the sharing of data between TOM systems, and we plan to support two different modes. Perhaps the most natural form of data sharing is simply directly sending the data from one team to another. In the first instance, we're providing tools so that users of the toolkit will be able to click a button and send information about a specific target direct to another TOM, as well as sharing time series photometry and spectroscopic measurements. And I'll note here that this is an area where we are particularly keen to hear feedback from users. So if you have any suggestions about other information that is important to share, please do let me know. Of course, the owners of each TOM will retain complete control over their data. Before any information can be shared with another TOM, the administrators will need to exchange tokens that will allow secure logins between the TOMs, and they'll be able to configure that in advance. The administrators will also have fine-grained controls over the sharing permissions for both the targets and data products. So they'll be able to toggle on and off sharing any data at all with specific targets. And the data will then be exchanged through a REST framework as a JSON object. Now that mode of operation works well when there are just a few competing teams, but in a large field like multi-messenger astrophysics, where there's a lot of competing teams, they may be all working from different areas of physics, this rapidly becomes impractical. The teams may or may not be using TOM systems to manage their programs. They may have developed their own systems. And that means that the interfaces between the teams can be in many different formats. And in this scenario, a centralized system for sharing information is more practical. And of course, the Gaia Alerts Index itself is an archetypal example of one such platform. Oops. Similar issues have happened across astrophysics, and there are several platforms for data sharing already in use by different communities, some of which have been designed around specific science goals, such as the Minor Planet Center. And there are other examples, such as the Artemis system for microlensing. These platforms act both as an alert broker in the sense of delivering information about new discoveries to users, and also as a repository where teams can upload new observations, which then other observers can access in order to optimize their own follow-up program. And it's worth noting at this point that this differs from most of the alert brokers currently under development for Rubin Observatory's legacy survey of space and time. Those brokers have mostly focused on serving alert information, aggregated with existing catalogs where available, but in general, they are not scoped to allow user-provided data upload. The multi-messenger field does already use a number of tools for sharing information, but they have felt to have a number of limitations. The first is that information is distributed across a number of platforms. There are several very efficient alert brokers handling survey output rather than follow-up data, and each broker synthesizes a different set of catalog information. Of course, there are GCN notices and circulars and the astronomers' telegrams, and these provide a different mechanism for disseminating information from follow-up observations, but there is no common format and they're not easily machine readable. And that slows down the process of combining this information from different sources, and it means it isn't very scalable. In the meantime, the Apache Kafka protocol for handling streamed data has become more widespread, particularly for Rubin and for ZTF data. So there have been moves within the community to tend toward that standard. And I'd like to note that the GCN now offers a Kafka stream, for example. And so the TOM team have been working to add support for Kafka streams to the toolkit. Recently, the CIMA organization, of which LCO is a partner, have been developing Hopscotch, which is a cloud-based instance of a Kafka data stream for multi-messenger science, which supports a publish and subscribe paradigm, so that users can not only receive information about new alerts, but also publish back to the stream, a bit like a Twitter thread for alert information. And that allows users to share characterization data as well. Our team have developed Hermes, as you can see on the screen, which is a prototype messaging service that provides an interface where users will be able to submit almost any form of astronomical data, including free-form text, and the result will be then encoded in a standardized format and sent via the Kafka stream. This interface provides both a browser-based user interface, which you can see on the screen, but also an API, and that makes it easy to integrate with a TOM system. So I'd like to share a quick demo of the interface that we've developed for TOM systems to facilitate the follow-up of multi-messenger alerts and non-localized targets. And play. So here you can see a TOM system which has retrieved a list of non-localized events announced via the GraceDB, which acts as a broker for gravitational wave alerts. Links are included in the table, which take the user to a visualization of the event's localization presented by the treasure map system, and also to a corresponding entry in GraceDB itself for easy reference. If we return to the index, we can click through to the TOM's own page for an example event, which provides an overview of all of the available data for this particular event. The table includes a summary of updates from different observers and different facilities, and you can click on each entry to get more detailed information. In the right, you can see data harvested from the GRACE-DB, and the top bar provides a quick reference summary of the current classification probabilities. Scrolling down further, you can see the two candidate tables. This is because within the large localization regions for each detected event, there are a number of potential candidates, usually associated with galaxies. Follow-up teams coordinate observations of those targets in response to each alert, searching for signs of the optical counterparts. Once a target has been observed, it is either eliminated as a candidate or remains on the active list, where the TOM can then request further observations. And with the Hermes platform, observers will be able to programmatically publish the results of those observations back to the Kafka stream, where they'll be disseminated to the community in real time. And we expect to provide tools so that the information can be shared via the GCM and other services as well. So in addition to sharing data products, another important aspect to coordinating observations between teams is the ability to share information about planned or executed observations. For example, knowing that one telescope facility plans to observe a given set of targets can help other observers to then plan their own accordingly. And there are a few existing tools for this purpose, such as the treasure map system that I mentioned earlier, and also the virtual observatory TAP protocol VisObsLog. We plan to expand our set of visualization tools in the toolkit to support those services. We're also in the process of expanding the range of telescope facilities that the TOM can interface with. This aspect is driven in particular by the telescope facilities contributing time as part of the Rubin in Kind program, where we'll be able to support other observatories to develop TOM plugins for their telescopes, and we've formed several partnerships to achieve this. But we won't be limited to ground-based telescopes. NASA's SWIFT mission has recently provided an API which allows observers to programmatically submit target of opportunity requests. So we partnered with them and will provide an interface to this space telescope. Last but of course not least, a key to any useful software is to make it accessible to its users. So we've always placed a strong emphasis on supporting our user base. That takes a number of forms, including, of course, good quality documentation and answering inquiries from users. But we'd also plan to return to offering user workshops now that we can organize in-person meetings again. So to wrap up, our team have been working on some new tools to facilitate the follow-up of time domain and multi-messenger events. And we expect to release these in the next month with the next version of the TOM Toolkit. We've been focusing on tools for data sharing and coordination in particular, and I hope these will be useful for a wide range of science goals. The team's currently in the process of ramping up our development efforts thanks to support from the NSF, and that will include adding support for new telescope facilities and making sure that we support the rapidly evolving functionality of alert brokers ahead of the start of LSST. I will stop there and I'll be very happy to answer any questions. Thank you.
Thank you very much, Rachel. Do we have any questions from Zoom?
Let's see.
Okay, and from the audience? Not this time. Okay. Lukasz, I'm sorry.
Hi, Rachel. This is Lukasz. Just a comment that LCO has been always very productive in terms of coming up with great ideas. And we had Rachel's talk last year at our workshop, and since then there has been so many new things developed that my notepad is full of notes from your talk, and especially I'm very much interested in digging into the multi-messenger tools you mentioned in the TOM toolkit, which our Black Hole Tome is actually based upon. So we're definitely looking forward to the next release. Is there a place where we can read about the new ideas you have implemented there?
There certainly will be. We have a demo system which is online, and I believe it has some of the new tools implemented, but I don't want to swear to it because I know our software developers are in the process of packaging up that new release. So it will be out very shortly, and there will be a demo version online that you can play with before you implement it.
Okay, I'm really looking forward to that. So we'll take a look. Thanks.
Excellent. Thank you.
Thank you very much. Okay, so this is the end of the second day of our conference. So thank you very much for your attendance, questions, comments, and for all the speakers to give us an interesting talk. And let's have a break and see you tomorrow. Thank you.
Thank you, Karolina, for sharing. I don't think we have any serious announcements to make, except that we're done for today. And tomorrow we begin 9:30. So enjoy your evening. Bye.